Johann Carl Friedrich Gauss. Latin, Carolus Fridericus Gauss, was a German mathematician, who contributed significantly to many fields, including number theory, algebra, statistics, analysis, differential geometry, geodesy, geophysics, electrostatics, astronomy, and optics. Sometimes referred to as the Princeps mathematicorum and greatest mathematician since antiquity, Gauss had a remarkable influence in many fields of mathematics and science and is ranked as one of history's most influential mathematicians. Early years. Carl Friedrich Gauss was born on April 30, 1777 in Brunswick, in the Duchy of Brunswick-Wolfenbüttel TTEL, as the son of poor working-class parents. Indeed, his mother was illiterate and never recorded the date of his birth, remembering only that he had been born on a Wednesday, 8 days before the Feast of the Ascension, which itself occurs 40 days after Easter. Gauss would later solve this puzzle about his birth date in the context of finding the date of Easter, deriving methods to compute the date in both past and future years. He was christened and confirmed in a church near the school he attended as a child. Gauss was a child prodigy. There are many anecdotes about his precocity while a toddler, and he made his first groundbreaking mathematical discoveries while still a teenager. He completed Disquisitiones Arithmeticae, his magnum opus, in 1798 at the age of 21, though it was not published until 1801. This work was fundamental in consolidating number theory as a discipline and has shaped the field to the present day. Gauss's intellectual abilities attracted the attention of the Duke of Brunswick, who sent him to the Collegium Carolinum, which he attended from 1792 to 1795, and to the University of Gau-Paragraph-Tingen from 1795 to 1798. While at university, Gauss independently rediscovered several important theorems. His breakthrough occurred in 1796 when he showed that any regular polygon with a number of sides which is a Fermat prime can be constructed by compass and straight. This was a major discovery in an important field of mathematics. Construction problems had occupied mathematicians since the days of the ancient Greeks, and the discovery ultimately led Gauss to choose mathematics instead of philology as a career. Gauss was so pleased by this result that he requested that a regular heptadecagon be inscribed on his tombstone. The stonemason declined, stating that the difficult construction would essentially look like a circle. The year 1796 was most productive for both Gauss and number theory. He discovered a construction of the heptadecagon on March 30. He further advanced modular arithmetic, greatly simplifying manipulations in number theory. On April 8 he became the first to prove the quadratic reciprocity law. This remarkably general law allows mathematicians to determine the solvability of any quadratic equation in modular arithmetic. The prime number theorem, conjectured on 31 May, gives a good understanding of how the prime numbers are distributed among the integers. Gauss also discovered that every positive integer is representable as a sum of at most 3 triangular numbers on July 10 and then jotted down in his diary the famous note, II xi male, ishi. Numa equals AIA plus AIA plus AI. On October 1 he published a result on the number of solutions of polynomials with coefficients in finite fields, which 150 years later led to the Weil conjectures. Middle years. In his 1799 doctorate in absentia, a new proof of the theorem that every integral rational algebraic function of one variable can be resolved into real factors of the first or second degree, Gauss proved the fundamental theorem of algebra which states that every non-constant single-variable polynomial with complex coefficients has at least one complex root. Mathematicians including Jean-Laurent D'Alembert had produced false proofs before him, and Gauss's dissertation contains a critique of D'Alembert's work. Ironically, by today's standard, Gauss's own attempt is not acceptable, owing to implicit use of the Jordan curve theorem. However, he subsequently produced 3 other proofs, the last one in 1849 being generally rigorous. His attempts clarified the concept of complex numbers considerably along the way. Gauss also made important contributions to number theory with his 1801 book Disquisitiones Arithmeticae, which, among things, introduced the symbol a per mil for congruence and used it in a clean presentation of modular arithmetic, contained the first two proofs of the law of quadratic reciprocity, developed the theories of binary and ternary quadratic forms, stated the class number problem for them, and showed that a regular heptadecagon can be constructed with straight and compass. In that same year, Italian astronomer Giuseppe Piazzi discovered the dwarf planets Ceres. Piazzi could only track Ceres for somewhat more than a month, following it for 3 degrees across the night sky. Then it disappeared temporarily behind the glare of the sun. Several months later, when Ceres should have reappeared, Piazzi could not locate it. The mathematical tools of the time were not able to extrapolate a position from such a scant amount of data. 3 degrees represent less than 1% of the total orbit. Gauss, who was 24 at the time, heard about the problem and tackled it. After 3 months of intense work, he predicted a position for Ceres in December 1801 just about a year after its first sighting and this turned out to be accurate within a half degree when it was rediscovered by Franz Xaver von Zach on December 31 at Gotha, and 1 day later by Heinrich Olbers in Bremen. Gauss's method involved determining a conic section in space, given one focus and the conic's intersection with 3 given lines and given the time it takes the planet to traverse the arcs determined by these lines. This problem leads to an equation of the 8th degree, of which one solution, the Earth's orbit, is known. The solution sought is then separated from the remaining 6 based on physical conditions. In this work Gauss used comprehensive approximation methods which he created for that purpose. One such method was the fast Fourier transform. While this method is traditionally attributed to a 1965 paper by J. W. Cooley and J. W. Tukey, Gauss developed it as a trigonometric interpolation method. His paper, Theoria Interpolationis Methodo Nova Tractata, was only published posthumously in Volume 3 of his collected works. This paper predates the first presentation by Joseph Fourier on the subject in 1807. Zach noted that without the intelligent work and calculations of Dr. Gauss we might not have found Ceres again. Though Gauss had up to that point been financially supported by his stipend from the Duke, he doubted the security of this arrangement, and also did not believe pure mathematics to be important enough to deserve support. Thus he sought a position in astronomy, and in 1807 was appointed Professor of Astronomy and Director of the Astronomical Observatory in Ɡaʊs, a post he held for the remainder of his life. The discovery of Ceres led Gauss to his work on the theory of the motion of planetoids disturbed by large planets, eventually published in 1809 as Theoria Motus Corporum Coelestium in section Ibis Conicis Solum Ambientum. In the process, he so streamlined the cumbersome mathematics of 18th-century orbital prediction that his work remains a cornerstone of astronomical computation. It introduced the Gaussian gravitational constant, and contained an influential treatment of the method of least squares, a procedure used in all sciences to this day to minimize the impact of measurement error. Gauss proved the method under the assumption of normally distributed errors. The method had been described earlier by Adrien Marie Legendre in 1805, but Gauss claimed that he had been using it since 1795. In 1818 Gauss, putting his calculation skills to practical use, carried out a geodesic survey of the Kingdom of Hanover, linking up with previous Danish surveys. To aid the survey, Gauss invented the heliotrope, an instrument that uses a mirror to reflect sunlight over great distances, to measure positions. Gauss also claimed to have discovered the possibility of non-Euclidean geometries but never published it. This discovery was a major paradigm shift in mathematics, as it freed mathematicians from the mistaken belief that Euclid's axioms were the only way to make geometry consistent and non-contradictory. Research on these geometries led to, among other things, Einstein's theory of general relativity, which describes the universe as non-Euclidean. His friend Farkas Wolfgang Bolyai, with whom Gauss had sworn brotherhood and the banner of truth as a student, had tried in vain for many years to prove the parallel postulate from Euclid's other axioms of geometry. Bolyai's son, János Bolyai, discovered non-Euclidean geometry in 1829. His work was published in 1832. After seeing it, Gauss wrote to Farkas Bolyai, "To praise it would amount to praising myself." For the entire content of the work coincides almost exactly with my own meditations which have occupied my mind for the past 30 or 35 years. This improved statement put a strain on his relationship with Janos Bolyai, but it is now generally taken at face value. Letters from Gauss years before 1829 reveal him obscurely discussing the problem of parallel lines. Waldo Dunnington, a biographer of Gauss, argues in ɡaʊs, Titan of Science that Gauss was in fact in full possession of non-Euclidean geometry long before it was published by Janos Bolyai, but that he refused to publish any of it because of his fear of controversy. The Geodetic Survey of Hanover, which required Gauss to spend summers traveling on horsebacks for a decade, fueled Gauss's interest in differential geometry, a field of mathematics dealing with curves and surfaces. Among other things he came up with the notion of Gaussian curvature. This led in 1828 to an important theorem, the Theorema egregium, establishing an important property of the notion of curvature. Informally, the theorem says that the curvature of a surface can be determined entirely by measuring angles and distances on the surface. That is, curvature does not depend on how the surface might be embedded in three-dimensional space or two-dimensional space. In 1821, he was made a foreign member of the Royal Swedish Academy of Sciences, later years and death. In 1831 Gauss developed a fruitful collaboration with the physics professor Wilhelm Weber, leading to new knowledge in magnetism and the discovery of Kirchhoff's circuit laws in electricity. It was during this time that he formulated his namesake law. They constructed the first electromechanical telegraph in 1833, which connected the observatory with the Institute for Physics in ɡaʊs. Gauss ordered a magnetic observatory to be built in the garden of the observatory, and with Weber founded the Monte which supported measurements of Earth's magnetic field in many regions of the world. He developed a method of measuring the horizontal intensity of the magnetic field which was in use well into the second half of the 20th century, and worked out the mathematical theory for separating the inner and outer sources of Earth's magnetic field. In 1840, Gauss published his influential Attribution, in which he gave the first systematic analysis on the formation of images under a paraxial approximation. Among his results, Gauss showed that under a paraxial approximation an optical system can be characterized by its cardinal points, and he derived the Gaussian lens formula. In 1854, Gauss notably selected the topic for Bernhard Riemann's now famous Habilitation-Vortrag, über die Hypothesen, Welche der Geometrie zugrunde. On the way home from Riemann's lecture, Weber reported that Gauss was full of praise and excitement. Gauss died in ɡaʊs, in the Kingdom of Hanover in 1855 and is interred in the Albany Friedhof Cemetery there. Two individuals gave eulogies at his funeral, Gauss's son-in-law Heinrich Ewald and Wolfgang Sartorius von Waltershausen, who was Gauss's close friend and biographer. His brain was preserved and was studied by Rudolf Wagner, who found its mass to be 1,492 grams and the cerebral area equal to 219,588 square millimeters. Highly developed convolutions were also found, which in the early 20th century was suggested as the explanation of his genius. Religious views. Gauss biographer G. Waldo Dunnington describes Gauss's religious views on these terms. For him science was the means of exposing the immortal nucleus of the human soul. In the days of his full strength it furnished him recreation and, by the prospects which it opened up to him, gave consolation. Toward the end of his life it brought him confidence. Gauss' God was not a cold and distant figment of metaphysics, nor a distorted caricature of embittered theology. To man is not vouchsafed that fullness of knowledge which would warrant his arrogantly holding that his blurred vision is the full light and that there can be none other which might report truth as does his. For Gauss, not he who mumbles his creed, but he who lives it, is accepted. He believed that a life worthily spent here on earth is the best, the only, preparation for heaven. Religion is not a question of literature, but of life. God's revelation is continuous, not contained in tablets of stone or sacred parchment. A book is inspired when it inspires. The unshakable idea of personal continuance after death, the firm belief in a last regulator of things, in an eternal, just, omniscient, omnipotent God, formed the basis of his religious life, which harmonized completely with his scientific research. Apart from his correspondence, there are not many known details about Gauss' personal creed. Many biographers of Gauss disagree with his religious stance, with bar one Courtelet and others who considered him a deist with very unorthodox impressions, while Dunnington points out that he was, at least, a nominal Lutheran. In connection to this, there's a record of a conversation between Rudolf Wagner and Gauss, in which they discussed William Whewell's book of the Plurality of Worlds. In this work, Whewell had discarded the possibility of existing life in other planets, on the basis on theological arguments, but this was a position with which both Wagner and Gauss disagreed. Later Wagner explained that he did not fully believe in the Bible, though he confessed that he envied those who were able to easily believe. This later led them to discuss the topic of faith, and in some other religious remarks, Gauss said that he had been more influenced by theologians like Paul Gerhardt, than by Moses. Other of his religious influences included Wilhelm Bragg, Johann Peter Zarwan Kortesmilch, and the New Testament. Dunnington further elaborates on Gauss's religious views by writing, Gauss' religious consciousness was based on an insatiable thirst for truth and a deep feeling of justice extending to intellectual as well as material goods. He conceived spiritual life in the whole universe as a great system of law penetrated by eternal truth, and from this source he gained the firm confidence that death does not end all. Gauss declared he firmly believed in the afterlife, and saw spirituality as something essentially important for human beings. He was quoted stating, "The world would be nonsense, the whole creation an absurdity without immortality," and for this statement he was severely criticized by the atheist Jürgen Darwin Kortering, who judged him as a narrow superstitious man. Though he was not a churchgoer, Gauss strongly upheld religious tolerance, believing that one is not justified in disturbing another's religious belief, in which they find consolation for earthly sorrows in time of trouble. When his son Eugene announced that he wanted to become a Christian missionary, Gauss approved him, saying that regardless of the problems within religious organizations, missionary work was a highly honorable task. Family. Gauss's personal life was overshadowed by the early death of his first wife, Johanna Osthoff, in 1809, soon followed by the death of one child, Louis. Gauss plunged into a depression from which he never fully recovered. He married again, to Johanna's best friend named Friederike Wilhelmine Waldeck, but commonly known as Minna. When his second wife died in 1831 after a long illness, one of his daughters, Therese, took over the household and cared for Gauss until the end of his life. His mother lived in his house from 1817 until her death in 1839. Gauss had 6 children. With Johanna, his children were Joseph, Wilhelmina and Louis. With Minna Waldeck he also had 3 children, Eugene, Wilhelm and Therese. Eugene shared a good measure of Gauss's talent in languages and computation. Therese kept house for Gauss until his death, after which she married. Gauss eventually had conflicts with his sons. He did not want any of his sons to enter mathematics or science for fear of lowering the family name. Gauss wanted Eugene to become a lawyer, but Eugene wanted to study languages. They had an argument over a party Eugene held, which Gauss refused to pay for. The son left in anger and, in about 1832, emigrated to the United States, where he was quite successful. Wilhelm also settled in Missouri, starting as a farmer and later becoming wealthy in the shoe business in St. Louis. It took many years for Eugene's success to counteract his reputation among Gauss's friends and colleagues. See also the letter from Robert Gauss to Felix Klein on September 3, 1912. Personality. Carl Gauss was an ardent perfectionist and a hard worker. He was never a prolific writer, refusing to publish work which he did not consider complete and above criticism. This was in keeping with his personal motto Pauca sed matura. His personal diaries indicate that he had made several important mathematical discoveries years or decades before his contemporaries published them. Mathematical historian Eric Temple Bell estimated that, had Gauss published all of his discoveries in a timely manner, he would have advanced mathematics by 50 years. Though he did take in a few students, Gauss was known to dislike teaching. It is said that he attended only a single scientific conference, which was in Berlin in 1828. However, several of his students became influential mathematicians, among them Richard Dedekind, Bernhard Riemann, and Friedrich Bessel. Before she died, Sophie Germain was recommended by Gauss to receive her honorary degree. Gauss usually declined to present the intuition behind his often very elegant proofs. He preferred them to appear out of thin air, and erased all traces of how he discovered them. This is justified, if unsatisfactorily, by Gauss in his Disquisitiones Arithmeticae, where he states that all analysis must be suppressed for sake of brevity. Gauss supported the monarchy and opposed Napoleon, whom he saw as an outgrowth of revolution. Anecdotes. There are several stories of his early genius. According to one, his gifts became very apparent at the age of 3 when he corrected, mentally and without fault in his calculations, an error his father had made on paper while calculating finances. Another famous story has it that in primary school after the young Gauss misbehaved, his teacher, J.G. Bar 1/4 ttner, gave him a task: add a list of integers in arithmetic progression. As the story is most often told, these were the numbers from 1 to 100. The young Gauss reputedly produced the correct answer within seconds, to the astonishment of his teacher and his assistant Martin Bartels. Gauss's presumed method was to realize that pairwise addition of terms from opposite ends of the list yielded identical intermediate sums: 1 plus A100 equals A101, 2 plus A99 equals A101, 3 plus A98 equals A101, and so on, for a total sum of 50 A101 equals A5050. However, the details of the story are at best uncertain. Some authors, such as Joseph Rotman in his book A First Course in Abstract Algebra, question whether it ever happened. According to Isaac Asimov, Gauss was once interrupted in the middle of a problem and told that his wife was dying. He is purported to have said, "Tell her to wait a moment till I'm done." This anecdote is briefly discussed in G. Waldo Dunnington's Gauss, Titan of Science, where it is suggested that it is an apocryphal story. He referred to mathematics as the queen of sciences, and supposedly once espoused a belief in the necessity of immediately understanding Euler's identity as a benchmark pursuant to becoming a first-class mathematician. Commemorations. From 1989 through 2001, Gauss is portrayed, a normal distribution curve and some prominent paragraph Tingen buildings were featured on the German 10-mark banknote. The reverse featured the approach for Hanover. Germany has also issued 3 postage stamps honoring Gauss. One appeared in 1955 on the 100th anniversary of his death. 2 others, Nos. 1246 and 1811, in 1977, the 200th anniversary of his birth. Daniel Kahneman's 2005 novel Die Vermessung der Welt, translated into English as Measuring the World, explores Gauss's life and work through a lens of historical fiction, contrasting them with those of the German explorer Alexander von Humboldt. A film version directed by Detlev Buck was released in 2012. In 2007, a bust of Gauss was placed in the Walhalla Temple. Things named in honor of Gauss include the Gauss Prize, one of the highest honors in mathematics, Gauss's law and Gauss's law for magnetism, 2 of Maxwell's 4 equations. Degaussing, the process of eliminating a magnetic field. The CGS unit for magnetic field was named Gauss in his honor. The crater Gauss on the Moon, asteroid 1001 Gaussier, the ship Gauss, used in the Gauss expedition to the Antarctic, Gaussberg, an extinct volcano discovered by the above-mentioned expedition, Gauss Tower, an observation tower in Drunsfeld, Germany, in Canadian junior high schools, an annual national mathematics competition administered by the Center for Education in Mathematics and Computing is named in honor of Gauss, in University of California, Santa Cruz, in Crown College, a dormitory building is named after him, the Gauss House, an NMA Center at the University of Utah, the Carl Friedrich Gauss School for Mathematics, Computer Science, Business Administration, Economics, and Social Sciences of Braunschweig University of Technology, the Gauss Building at the University of Idaho, the Carl Friedrich Gauss Gymnasium in Worms, Germany. In 1929 the Polish mathematician Marian Rejewski, who would solve the German Enigma cipher machine in December 1932, began studying actuarial statistics at ɡaʊs. At the request of his Potsdam University professor, Zsisai Krygorski, on arriving at ɡaʊs, Raduski laid flowers on Gauss's grave. Writings, 1799, doctoral dissertation on the fundamental theorem of algebra, with the title, Demonstratio nova theorematis omnem functionum algebrae sam rationalem integram unius variabilis in factors reals me vel secundi gradus resolvi posse of the first or second degree, 1801, Disquisitiones Arithmeticae. A German translation by H. Maser unter Zachandina 1/4 paragraph here Arithmetique. New York, Chelsea 1965. ISBN A0-8284-0191-8, pp. 1 Euro 453. English translation by Arthur A. Clarke. Disquisitiones Arithmeticae. New York, Springer. 1986. ISBN A0-387-96254-9A. 1808, Theorematis Arithmeticae Demonstratio Nova. ɡaʊs. Comment. Socrates Sci. ɡaʊs. 16a. German translation by H. Maser unter Zachandina 1/4 paragraph here Arithmetique. New York, Chelsea 1965. ISBN A0-8284-0191-8, pp. 457 Euro 462, introduces Gauss's lemma, uses it in the third proof of quadratic reciprocity, 1809, Theoria motus corporum coelestium in sectionibus conicis solem ambientium, theory of the motion of heavenly bodies moving about the Sun in conic sections, reprinted 1963, Dover, New York, 1811, Summatio seria unquaerendam singularium. ɡaʊs. Comment. Socrates Sci. ɡaʊs. A. German translation by H. Maser unter Zachandina 1/4 paragraph here Arithmetique. New York, Chelsea 1965. ISBN A0-8284-0191-8, pp. 463 Euro 495, determination of the sign of the quadratic Gauss sum, uses this to give the fourth proof of quadratic reciprocity, 1812, Disquisitiones Generales circa seriem infinitam, 1818, Theorematis fundamentalis in doctrina de residui quadraticis demonstrations et applications novae. ɡaʊs. Comment. Socrates Sci. ɡaʊs. A. German translation by H. Maser unter Zachandina 1/4 paragraph here Arithmetique. New York, Chelsea 1965. ISBN A0-8284-0191-8, pp. 496 Euro 510, fifth and sixth proofs of quadratic reciprocity, 1821, 1823 and 1826, Theoria combinationis observationum erroribus minimis Blockschrei. Drehab und Lungen betreffend die Wahrscheinlichkeitsrechnung als Grundlage des Gaußschen Fortpflanzungssatzes. English translation by G. W. Stewart, 1987, Society for Industrial Mathematics. 1827, Disquisitiones Generales circa superficies curvae, Commentations Societatis Regiae Scientiarum Gothengesis Recentiores. Volume 6, ppA 99 Euro 146. General Investigations of Curved Surfaces Raven Press, New York, translated by A. M. Hilterbeidl and J. C. Moorhead, 1828, Theoria Residuorum biquadraticorum, Commentatio Prima. ɡaʊs. Comment. Socrates Sci. ɡaʊs. 6a. German translation by H. Maser unter Zachandina 1/4 paragraph here Arithmetique. New York, Chelsea 1965. ISBN A0-8284-0191-8, pp. 511 Euro 533, Elementary Facts About Biquadratic Residues, proves one of the supplements of the law of biquadratic reciprocity, 1832. Theoria residuorum biquadraticorum, commentatio secunda. ɡaʊs tingen, comment. Soc regeri sci, ɡaʊs tingen 7a. German translation by H. Maser unter Zachungena 1/4 Beha paragraph here Arithmetic. New York, Chelsea 1965. ISBN A0-8284-0191-8 ppA 534 Euro 586, introduces the Gaussian integers, states the law of biquadratic reciprocity, proves the supplementary law for 1 plus I, 1843/44, unter Zachungena 1/4 Bed Gegenste currency NDE der Haar paragraph Herrenjede currency Psi. Abendlungen der Car paragraph Niglichen Gesellschaft der Wissenschaften Gar paragraph Tingen. Zitterband, ppA 3 Euro 46 and 1846/47, unter Zachungena 1/4 Bed Gegenste currency NDE der Haar paragraph Herrenjede currency Psi. Abendlungen der Car paragraph Niglichen Gesellschaft der Wissenschaften Gar paragraph Tingen. Dritterband, ppA 3 Euro 44, Mathematisches Tagebuch 1796 Euro 1814, Ostwaldsklassiker, Harry Deutsch Verlag 2005, Mittenmerkingen von Neumann, ISBN 978-3-8171-3402-1. Gauss's collective works are online here. This includes German translations of Latin texts and commentaries by various authorities. See also, Carl Friedrich Gauss Prize, German inventors and discoverers, list of topics named after Carl Friedrich Gauss, Romanticism in Science, notes. Further reading, Bar 1/4 Lehr, Walter Kaufmann. Gauss, A Biographical Study. Springer Verlag. ISBN A0-387-10662-6. Dunnington, G. Waldo Carl Friedrich Gauss, Titan of Science. The Mathematical Association of America. ISBN A0-88385-547-X. OCLCA 53933110. Gauss, Carl Friedrich. Disquisitions Arithmetic et.r. Arthur A. Clarke. Yale University Press. ISBN A0-300-09473-6. Hall, Tord. Carl Friedrich Gauss, A Biography. Cambridge, Massachusetts, MIT Press. ISBN A0-262-08040-0. OCLCA 185,662,235. Kahilman, Daniel. Die Vermessung der Welt. Rowohlt. ISBN A3-498-03528-2. OCLCA 144,590,801. Sartorius von Waltershausen, Wolfgang. Gauss, A Memorial. Simmons, J. The Giant Book of Scientists, The 100 Greatest Minds of All Time. Sydney, The Book Company. Tent, Margaret. The Prince of Mathematics, Carl Friedrich Gauss. A. K. Peters. ISBN A1-56881-455-0. External links, media related to Johann Carl Friedrich Gauss at Wikimedia Commons, works related to Carl Friedrich Gauss at Wikisource, quotations related to Carl Friedrich Gauss at Wikiquote, Carl Friedrich Gauss at planetmath.org. Complete works, Gauss and his children, Gauss biography, Carl Friedrich Gauss at the Mathematics Genealogy Project, Carl Friedrich Gauss a Eurobiography at Fermat's Last Theorem blog, Gauss, Mathematician of the Millennium, by Johann Carl G. N. Schmidhuber, English translation of Waltershausen's 1862 biography, Gauss General website on Gauss, MNRAS 1680 obituary, Carl Friedrich Gauss on the 10 Deutsche Mark banknote, O'Connor, John J. Robertson, Edmund F., Carl Friedrich Gauss, Maxsheta History of Mathematics Archive, University of St Andrews. Carl Friedrich Gauss in the series A Brief History of Mathematics on BBC 4, Grimes, James. 50/50 and a Gauss trick. Numberphil. Brady Heron A.